This is the modulation. Okay, before we starting the modulation technique, I just want to review a little bit about the digital signal transmission and the basic components of the communication. Okay, so this is what we learned. Right, so you learn about signal and then you understand the composite signal. Do you understand? I hope you understand already what is the digital signal and what is the bandwidth of it and what should be the bandwidth of communication channel, right? But anyway, before having the lectures of modulation, it's good to review a little bit about it. Okay, so this is the two approach of the digital communication. So if you remember, there are two types or approaches. One is baseband transmission, and the second one is broadband transmission. So what is the baseband transmission? So this one is actually like very easy way. So it means that after you have the information from the generating source, for example, the information from computer, and then you just send it as is without changing the shape of the signal to the channel or to the medium. And then the information is like transmitted to the destination. But by doing this, the channel have to provide whole capacity for just transmitting one information. And then the baseband transmission requires that we have a low pass channel. So the channel should be start from 0 Hertz until some certain frequency. Okay, so this is a comparison of the wide bandwidth and the narrow bandwidth. So it depends on how big of the information. But anyway, by transmitting baseband signal, you need to have the things we call low pass channel. So for low pass channel, the important thing is that the channel starting at the 0 Hertz. Okay, but this is not like practical in the real situation because as I mentioned the channel should provide just whole capacity for sending only one information. So in practical, this approach is more proper. It is called broadband transmission. Broadband transmission sometimes is called modulation. This technique need to change the digital signal to an analog signal for transmission. And by doing this, the modulation allow us to use the band pass channel. This is the channel with a bandwidth that does not start from 0. For example, you can see from this frequency spectrum, it ranges from F1 to F2, and F1 does not need to start from 0. Okay, so this is more practical because in the real situation, um, the application use different bandwidth. For example, for FM, it ranges from 88 megahertz until 800 megahertz. And then one station divided by like having a bandwidth of 200 kHz. So you can observe that by using application of FM broadcasting or TV broadcasting, the information need just band pass channel, which need a bandwidth start from not 0 Hertz. Okay, so this is the transmission technique that is more proper. More practical use in the real scenario. So this is the pictures that try to describe how the information from originating or the source need to be changed. So this one is the input signal data, means the data from the source. And then before this signal is transmitted to the receiver, it needs to change to analog signal. So this one is like, okay, original one is digital signal, but we need to change it to be analog signal. Okay, this technique is called modulation. So changing the digital signal to an analog signal for transmission. And then, okay, so this one is kind of like the digital signal. If you remember the bandwidth of digital signal approach to infinity hertz, but there's no channel that fits to infinity hertz of bandwidth. Okay, so we need to do something. We need the carrier. Carrier. Carrier means the things that carry the information to the destination. The carrier in communication we call carrier signal, which is the actually sinusoidal wave or sine cosine wave, which is the analog signal, right? So it's kind of like this information is encoded by this carrier, and the shape become the analog signal. For example, this one, okay, you see, but you can observe that this original signal, the pink one, we can observe it as the envelope of the analog signal, right? So the receiver can recognize that, okay, by observing the envelope of the analog signal, that is can be like decode to be the information that is sent from the source. Okay, so it's like, okay, observe at the receiver side, and then the receiver detect just the envelope, and then it can be detected that, okay, this one is the information that actually sent from the source. Okay, so this is the broadband transmission. Okay, and if you take a look, the basic component of the communication, we study about this at the very beginning lectures, right? So the communication component composed of actually three main components, right? So one is the transmitter, right? And then the second one is the channel, and the third one is the receiver. For the channel, it can be wired or wireless, right? But for IoT module, most of the channel we use is wireless channel. For the wireless channel, the frequency that is proper to be transmitted is the very, very high frequency. So it's more than like UHF or VHF and above. Okay, so if you take a look at each side, I mean the devices, for example, the transmitter side, you have to have the source, right? The source means that it generates the information. And then the information can be analog, for example, voice, human voice, or the information from the computer can be digital, right? But this either both analog and digital need to be changed or like modify the shape that more proper to the channel. So if you take a look in the transmission system, you have to have this block diagram. This is called the modulator. So the modulator is actually the device that modifies the input signal characteristic, which is more suitable to transmit to the air. Okay, say for example, in the previous slide, you change it to be analog signal like this, and then by sending the digital one, you can observe the envelope of analog signal, which is the output of the modulator, right? And then you transmit it to the channel. But before you transmit it at the channel, you have to make it strong. I mean, you have to increase the power, so the amplifier is needed. Okay, and for the transmitter in this sense is actually the antenna. If we consider as the wireless channel, it will be the antenna. So you have the proper signal, you make it strong by adding more power and then transmit it via the antenna. And then the antenna will propagate as a wave, okay? And this wave is actually carry the information, like the carrier carry your information and is sent to the channel. And then if you take a look at the receiver side, the wave that is transmit arrive at the receiver. Oh, sorry, should be this way. So the antenna at the receiver side will capture the wave, and then along the way in the channel, there's maybe obstacle or things that distort the signal. So first, before you detect back the original signal, you have to make it strong. So adding more power, and then you use the technique called demodulator to detect back the signal that transmit from the transmitter. Okay, so the concept is that today you understand that you have the original signal, you understand the carrier, and then you understand a variety of the modulation technique. Okay, so in this case, in these two slides, I just want to say that at the transmitter side, you need a modulator, and at the receiver side, you need the demodulator. Okay, so let's start the basic modulation techniques. So the modulation technique is like, as I explained in previous slide, you have a transmitter or sender, right? And then in this example, this computer generates the bit stream. This is the example of the bit stream, which is the digital data stream, right? For example, 11001 is the information that this computer need to send to the receiver. But if you want to send it via Wi-Fi, for example, Wi-Fi. Wi-Fi means wireless LAN, right? So you need to send the information wirelessly. And then as I mentioned, wireless channel need and support a high frequency of the signal. But the digital data, if you remember, if you send a binary, which is 11001, you can represent it into like two level of the voltage, right? You may define that the positive voltage is bit 1 and the zero voltage is bit 0, right? So if you want to transmit 11001, so this is not proper to send to the channel as is. You have to map it to the higher analog signal, which is called carrier frequency. So this is another example, another analog signal, which is different from this example. So this one, you can see that the information is encoded to the amplitude, right? But in this case, in this example, we can observe that the analog signal have the constant amplitude. I mean, constant for bit 1, but it changed to be 0 when the 0 comes. Actually, this is ASK, but the previous one is called AM. I will explain it later what are different between these two. But anyway, okay, we have the original data. We need to change the shape to be analog signal, and the analog signal arrive at the receiver side. So the demodulator will detect back 11001. Okay, so the definition is that map the data into the signal which is suitable for transmission medium. That signal is called the carrier, as I mentioned. Okay, the carrier wave has the frequency of the wireless channel used for communication. So it depends on the technology used. For example, if you want to send it using Wi-Fi protocol. Wi-Fi protocols use 2.4 gigahertz, right? So the carrier would be 2.4, around 2.4 gigahertz. But if you want to send the information to 5G, if you send to 5G, the carrier or the frequency, it actually is range from like 700 megahertz until 2000 megahertz. Okay, so but anyway, so it depends on what technology or what IoT module you use. If you use Wi-Fi, of course, the digital signal should be mapped into 2.4 gigahertz. But if you want to send it to cellular network, say 5G, you may map to the range of the VHF frequency. Okay, but anyway, this one is a higher is a high RF frequency that is proper for communication. The modulation process is to change a certain property of the carrier. So with this sentence means that we use a carrier or say the vehicle to bring your information to the destination, right? So the carrier, as mentioned somewhere, not this slide, but I can say that the carrier is the shape of sine or cosine wave, which is periodic signal, right? This is the simplest signal, right? In like, this is not can be like decomposed to any shape of the signal. This is the simplest version of the periodic signal. And if you remember, the periodic signal have three characteristics, right? Three characteristic means you can observe the amplitude, which is the high peak, right? From the zero to up or high. So this is the amplitude. And the second characteristic is the carrier. The frequency means the number of cycle of the sine wave or cosine wave in 1 second. And then the last characteristic is the phase, right? So the phase means that at the time zero, what is the position of the signal? So if in this figure, at t equal to 0, the phase start here, right? So this signal has a 0 degree of phase. Okay, so we use this characteristic to define different type of the modulation techniques. Okay, this slide is just want to show that the modulation technique is like move the frequency of the baseband signals, baseband data stream to a frequency of the transmission channel. So for this signal, baseband data stream is the user information, right? Or the information that is generated from the source. The frequency of this signal is very, very low frequency. Say you have originally have F as the frequency of the baseband, and then you want to send it with the carrier, right? With the carrier or the carrier. The carrier will have the frequency called omega c. So omega here represent 2 pi fc. So actually is angular frequency. This is angular frequency. The unit of angular frequency is radian. But usually we get used to the frequency represented by F, right? So this one, the unit will be hertz. So the angular frequency, the omega c equal to pi fc. So what it means for the first sentence is that your information, which has a low frequency, need to move to the frequency of the carrier. So if you take a look at spectrum, you understand the spectrum, right? So say if you have your information as a baseband. Maybe the frequency is very low. For example, my voice now it's captured with a microphone, right? The human voice is actually range from 0 hertz to 4K hertz. So at the middle of the bandwidth, we call the center frequency. So this center frequency, if it mix with the carrier, say, for example, I want to like use a Wi-Fi as the channel. So the frequency of the carrier should be something like 2.4 gigahertz. So this one will be represented as carrier frequency. So what it means here is that if I want to send my voice, which have the center frequency of, in this case, 2K hertz, right? The middle frequency between 0 hertz and 4K hertz is 2K hertz. And then if we modulate with the carrier, the frequency of 2K hertz will move to the center of carrier frequency. So in this case, FC will be 2.4. Okay, so if you take a look in the frequency domain, you can observe that the data that propagate into the channel have a frequency of the carrier 1. Okay, this is what for the first sentence means. And the second sentence, to multiply or mix the baseband signal with the carrier frequency. So this is called the technique of carrier modulation. We need the carrier for like to be a vehicle to carry your information. And the spectrum is shown like in this graph. Okay, so there's many techniques of the modulation. It depends on what type of the carrier signal. So I can say that if we take a look at carrier, actually the carrier is the signal. It can be analog, it can be digital. But in this lecture, as I mentioned, for wireless, for IoT-based application, most of the application use wireless channel, and the wireless channel work well with the analog high frequency. So in this case, we will focus on this part. But anyway, the carrier can be digital one as well, can be a higher frequency, but is the digital type. But the digital type, if you remember, it requires very wide bandwidth. So this technique is proper to send in like the wide communication, like optic fiber. Okay. But anyway, so let's focus on here. So if the carrier is analog, okay, and as I explained, the characteristic of the periodic signal is there are 3 characteristics, right? Amplitude, frequency, and phase. And if amplitude of the analog carrier change, we will call amplitude modulation. But if the frequency of the carrier change, we will call frequency modulation. But if the phase of the carrier change, we will call phase modulation. All right. But if you see these columns, there are 2 columns. What are different between these two? So these 2 columns represent the type of information signal, info signal. So the signal that you want to transmit, if it's analog or if it's digital, okay? So if the input is analog, the modulation by changing the amplitude of the carrier we call FM. But if the information is the digital, and then the amplitude of the carrier change we will call ASK, and so on. Okay, so but nowadays most of the information signal is digital, and then we want to send the digital signal than sending the analog, because it's like can can work well in the noise channel. So most of the application use the digital information to transmit into the channel, and the carrier will be analog. So today I will focus on these three, which is ASK, FSK, and PSK. All right. Okay, let's start. What are different between those three? But before that, if you take a look in the table, you can see that there's many techniques, right? AM, FM, PM, SK, FSK, PSK. So if you want to design a communication, you may ask the questions like, what modulation technique is the best? So it depends on the choice of it depends on your objective. If you want it to make very easy, you may choose amplitude modulation. If you concern a noise tolerance, you may consider to have FM or PM, phase shift keying. Or if you concern about channel bandwidth, you want to save a bandwidth, you may consider to use FM or other things than use the amplitude modulation. So I will explain each technique about these three, okay? And there's a two well-known analog modulation technique. So this is like to start learning the modulation technique, we may start from AM, FM, even if we do not use it in the IoT-based application, but this is a good start to learn what is it, each, how it works, okay? So let's start to know about what is the analog modulation, what is AM, okay? So the abbreviation is AM. Okay, let's take a look at these three signals. These three. The first one is called modulating signal. It's actually your information. You want to send this information to the channel actually, but it's not proper. If you take a look, the frequency is very low frequency, right? The number of cycle per the time duration is lower compared to other. And the second signal is called carrier. Carrier, as I mentioned, is often sine or cosine wave, okay, comparatively having a high frequency. And then by having a technique called AM, you can see here that the amplitude of the carrier change, okay? So this is a carrier, you take a look at this one, okay? And then the amplitude of the sine wave is constant, but by using AM modulation, the amplitude of this carrier signal change according to the information you want to send. You got my point, right? So, and then while the frequency and the phase of the carrier remain the same. So if you remember three characteristic, amplitude, frequency, and phase, right, of the sine wave. So in this case, frequency and phase still same. If you take a look, carrier signal and the output of modulator. So this is modulator. So the device that convert the red one into a blue one. So by using AM, the frequency and the phase of the carrier still same. So if you count the number of cycles, you see the number of cycles still same, right? The blue and the black have the same cycle per time duration. So frequency is same. How about phase? Phase of the black and the blue are same. So these two characteristics remain the same, but the amplitude of the carrier change, you see, is not constant anymore, but the amplitude of the black signal which is the carrier, change according to the amplitude of the original or modulating signal. So you can observe here that the envelope of the blue one is actually the shape of the red one, right? So this one is called AM signal. AM signal carry your information, which is the red one, by put it into a carrier. All right, so this is called AM. So this is the way to implement it. It's just use the multiplication. It's called multiplier. So this is the device, electronic device that just multiply between two signal. One is the original signal and another one is the signal generated from the device called oscillator. It generates high frequency of the sine wave called the carrier with FC, carrier frequency. And then multiplier means that these two signals just like multiply at each time instant. For example, if you want to multiply this T1, so this amplitude and this amplitude will be multiplied with each other, right? And it become the output. And then for each instant of time, so it multiply with each other. So this is the output. I mean, the blue one is the output. This is AM. Okay. And then if you take a look, the second pictures, the below one. So this represent frequency domain. So this is time domain, all right? If you still remember Fourier series, every signal can be represented in two domains. One is time domain. In the time domain, you can see the shape of the signal, right? Change according to time, but you cannot see what are frequency inside, right? Then if you want to take a look the spectrum, so you can use the frequency domain. So this is actually the same signal, this one and this one. And by using the frequency representation, you can observe that, okay, this blue one have the center frequency of FC. Okay, so originally the frequency is not FC, is we can say FM, for example, M is a message or information. Then frequency of FM is changed or is moved to FC. And then this is the range of the spectrum from here to here. Bandwidth of the AM, the blue one here, equal to B. B means the bandwidth of the original one. Okay, B is bandwidth of original one, but by multiply with the carrier. And we have the output of the AM, and then the bandwidth become twice. This is, you know, it just double bandwidth is may not good in terms of the spectrum efficiency. If I call spectrum efficiency, this is the word that engineer use to concern when they design the communication. Because what? Because the channel, I mean the frequency have the limited band, right? And then if you design to use AM, you know that you need the channel that have 2 times of the original one. So this is not good in the terms of spectrum efficiency because it wastes, I mean, it needs like double bandwidth. But if you consider about the ease of implementation, AM is good because it uses only the multiplier to multiply the message and the carrier together. So it's very easy to implement. Okay, so okay. To conclude in this slide, the bandwidth of AM become 2 times of original signal. Okay, this is the application of using AM modulation. So this is the example of AM broadcasting, radio broadcasting. Nowadays, I don't think you listen the music from AM broadcasting in the car, right? But anyway, this is kind of application. So for AM broadcasting, the range of application provide for this app, application is range from 530 kHz until 1700 kHz. And each station, each AM station, have 10 kHz bandwidth. So for the first station, it will start at 530. It will end 540 kHz, right? And the center frequency represent FC, mean the carrier frequency. So if the song from the station want to send to the channel, the song is like the human range, right? From 0 hertz until 4K hertz. And the middle is 2K hertz. Then if use modulation of AM, FM message frequency will move to the frequency of, in this case, of what, 535 kHz, right? So this is the center frequency, represent the carrier frequency. And one more application, one next technique is called FM. So this is analog modulation as well. Analog modulation means that the input is analog, the output is analog. AM is analog modulation, input is analog, output is analog. But this is another type of analog modulation we call FM. We have original signal, message signal, and it's called modulating signal. Example of audio signal, right? The shape is like the red one. And you have the carrier frequency, very high frequency compared to modulating signal. And then this is the output of modulator. This is called FM. You can observe here that the FM, by using FM modulation, frequency of the carrier change, right? So this is the carrier frequency, the black signal. This actually have the constant frequency, right? Along the way, along the time. But if you modulate the red one with the black one, and the output become blue one, the FM signal, if you take a look at FM signal, the frequency will vary, right? So sometimes it's very high frequency and sometimes that is low frequency. So the frequency of the FM responsible for the amplitude of the signal. So if the modulating signal have a high amplitude, then the carrier will have a high frequency at around this point. You see, around this point, this area have a high amplitude of modulating signal, and then characteristic of the carrier change to be higher frequency. And then if you observe the modulating signal, the amplitude is lower, reduce, right? Reduce and lower amplitude. And then the frequency of the carrier become like lower as well, right? So the FM, if you take a look, the output, which is FM signal, you can observe that the just frequency change, right? The frequency of the carrier change correspondingly as amplitude of the information signal change. So it depends on amplitude of the signal, the frequency of the carrier change, then the output become like the blue one. While the peak amplitude and the phase of the carrier remain the same. So if you take a look, the phase of the FM and the phase of the carrier be still same, right? And the phase same and amplitude is the same also. So the carrier have this A, right, amplitude. So the FM become A as well. So the characteristic of the carrier in this AM, the change is the frequency. So this is called FM. Frequency change according to the amplitude of the modulating signal. All right. So this is like if you plot this time domain into frequency domain. You can have like this. Okay, the bandwidth become not just 2B, but have this variety also. So the bandwidth of the FM will be very, very big because this is the composite signal, right? They're composed of many sign component if you decompose it, right? And then inside the bandwidth of the FM, there's many frequency, and the bandwidth of FM become very, very large. If you go back to AM, for bandwidth of AM is just 2 times of B. B means the bandwidth of the modulating signal. But for FM, there is some parameter in here. This is 1 plus B. B is usually equal to 4. It's called modulation index. So if B beta or B is 4, in this case, it become what? This is 5. 5 times 2 become 10. So you see, bandwidth of the FM become 10 times of the original signal. So if you consider about the spectrum use, maybe FM is not proper. But the good thing for FM is that the system prefer the constant amplitude, because when the transmitter send the constant amplitude along the way, and then the receiver can guess what happened to the signal easier by having AM. Okay, I just write down here. So if this is AM, okay, sending at the transmitter side, and if you compare sending by using FM here, the along the way have a channel with maybe have a noise, right? By having a noise, the amplitude of the AM may change times to time, and then we cannot observe easily that what happened with original signal, because we do not know that what is the real amplitude of the signal, because the amplitude change and fluctuate a lot. But if you send the constant envelope of the signal, for example, FM, you see, this is constant envelope, right? And then the receiver expect to receive the constant envelope, of course. But if not, there's a noise along the channel. And if the original signal, I mean, from the transmitter side is not constant, it easily to check that, oh, that is the, like, something happened with the original signal. So in the communication system, by having the constant envelope of the signal is more, is preferable than just have the like fluctuate of amplitude signal, because it's easier to detect the error, to say. So the good point again is that the FM have constant envelope, but the AM have vary amplitude, right? Different amplitude along the way. So it's very difficult to detect. But the bad things for AM is that it use really wide bandwidth. Okay, so it depends on the choice of the, depends on the objective of the usage. What is your concern? All right, so this is the following slide is just to explain in detail about the modulation index, but I think this is out of the scope of this subject. So if you guys want to study, you just read it, the two or three slides here, and then I hope that you may understand more what the modulation index is. All right, but I will not I will not focus more on in the detail for this one. Okay, so this is the FM broadcasting as the application. Okay, so if you observe in the car, if your car still have FM broadcasting receiver, you may see the range of the frequency starting from 88 megahertz and end with 108 megahertz. And the bandwidth, you can observe here that the bandwidth required much higher than AM. If you remember AM requires just 10K hertz, right? But for FM, one channel require 200K hertz because there's many frequency needed to be sent, right? And in the same manner, for middle frequency for each channel, it is called carrier frequency. Okay, that is the first stage of the explanation of modulation technique, in which the amplitude, I mean the modulating signal is analog นะคะ but as I mentioned now today, most of the information is converted to be digital information, right? By maybe using analog to digital converter like pulse code modulation that I already explained. And then, yeah, for transmitter side, we prepare digital signal to be sent. So now, from this slide, we are going to learn what happens if the input is digital. Input of the modulator is digital signal, okay? But anyway, the output of the modulator become analog. So sometimes in this case, it's called digital modulation or digital to analog modulation. Because the input is digital, the output will be analog, okay? So there are three main types of the digital modulation. The first one is amplitude shift keying. A here means the amplitude of the carrier change. And F here means the frequency of the carrier change. And P here represents the phase of the carrier change. So shift keying means like it shifts from the original version of it. Original version, as I mentioned, the carrier have the sine wave, is a sine wave, right? This is amplitude, and there's some frequency, and you can take a look at phase. So if amplitude of the carrier change, we call ASK. If the frequency of the carrier change, we call FSK. If the phase of the carrier change, we call PSK. And there's a higher modulation technique that combine both amplitude shift keying and phase shift keying. Means that both amplitude and phase of the carrier change. And then we can get like a higher data rate. It is called QAM, quadrature amplitude modulation. And there's many techniques. And if you ask what is the best technique, I cannot say, but I can summarize here that most commonly used modulation technique in traditional wireless network and also IoT-based application is GMSK or FSK and QPSK, which is 4PSK. These two, if you see the graph later, you can observe that both have constant envelope or constant amplitude. So this is very easy to detect at the receiver. Okay, constant envelope and amplitude. So that's the reason why these two are most picked to use in the application. Okay, let's see for each. But before that, just review a little bit about data rate. Okay, so I think you understand definition of bit rate or data rate already. But anyway, what is it, Ka? So the data rate is what? Rate means we compare in 1 second of time duration, right? And then if we call data, or in this case, bit, means that how many bits per second. So the number of bits per second we call bit rate or data rate. In this slide, it represents by n. And there's another word called baud rate. I think you may have heard this word during the lab with Ajahn Sumek. I'm not sure, but the baud rate has the relationship with bit rate. For the baud rate, represented by S, is the number of signal elements, or the signal element actually we sometimes call symbol per second. You see, we want to count the number of signal element in 1 second, so we call this baud rate. The unit of baud rate is bauds, not baud per second. This is the technical terms that represent the unit of the baud rate. We call bauds. And in analog transmission of digital data, the signal or baud rate is less than or equal to bit rate. So what it means here is that, okay, for example, if you, I think we can explain here. Okay, just see the equation first. This is the relationship between baud and bit rate. S is baud rate. In baud rate may have multiple bits in one symbol or one signal element. And then if you want to calculate baud rate, you can use this equation. N is the data rate and R is the number of bit per signal element. Okay, you can take a look this graph. So this is just the graph that you learned before, right? So the digital signal can be represented in multiple level, right? So the basic, the very basic technique is that we divided the level into 2 levels, like this figure. In this case, there are 2 levels. Say level 1 represent by 0 voltage, and level 2 represent by positive voltage. And bit 1 can be encoded at a positive voltage. So if you want to transmit bit 1, the level become positive voltage. And at 0, if you want to send bit 0, the signal, electrical signal becomes 0 volt. So when you observe this pink signal, which is encode the information of the digital, you can say that, oh, actually, this is the data stream of 1, 0, 1, 1, 0, 0, 0, 1. Okay, so you observe for each level, one level represent one signal element. So this is one signal element, or in this case, one signal element composed of 1 bit, right? One signal, the signal element sometimes we call symbol. It means that how many bits that you send for each level. So in this case, you send 1 bit at a time. So one symbol composed of only 1 bit. And there's a 2 levels are required, right? And then if you observe this graph, this is 1 second, right? If I ask you what is the bit rate and baud rate in figure A, in 1 second, how many bits can be sent? So there's 8 bits is sent in 1 second, right? So the bit rate become 8 bits per second. And how about baud rate? Since one symbol represents only 1 bit, in this case, bit rate and baud rate will be the same number. So if it asks you to answer what is the baud rate, you can say that the baud rate become 8 bauds. Okay, because bit rate and baud rate is the same number. How about this figure B. In figure B, there are 4 levels, right? So we can have 4 signal elements because one level represents one signal element. So in this case, we may define that level 1 represent the signal element of 0, 0. Level 2 can be represent 0, 1, 1, 0, 1, 1, right? 4 level can have 4 signal elements. So 4 signal element, for each element can have 2 bits. In the previous slide, this equation is used to calculate the number of level or number of symbol related to the number of bit, right? This is the number of bit. So in this case, there are 4 levels, sorry. There's 4 levels. So the number of bit per level can be 2 bits, right? I ask you the same question. What is the bit rate? What is the bit rate? If the signal is like this, the pink one is the signal you want to send, and then you encode it as a bit stream like this. Level 4 is 1, 1. So you send 1, 1 for this voltage, and then stop, and then send in this voltage, which is represented by 1, 0. And voltage of level 2 represent 0, 1, 0, 1, right? So for each level, you can send 2 bits. So this is faster than just using 2 level, right? This is the bit rate become twice, right? So each time duration, you can send 2 bits. So in total, 1 second, you can send 16 bits. So the bit rate becomes 16 bits per second. You can count how many bits can be sent in 1 second. So that's the bit rate, which is 16 bits per second in this case. How about baud rate? What is baud rate? Baud rate, you have to count the number of baud or number of signal element in 1 second. So we have to count this pack, right? This group, because each group represents signal element or symbol. So how many symbol or signal element in 1 second? So you can count easily 1, 2, 3, 4, 5, 6, 7, 8. So in this case, the baud rate become 8 bauds. But the bit rate is 16 bit per second, right? What is R? So R, if you go back here, R is the number of data of bit per signal element. But you may confuse because previously I used n represent the number of bit, but it's the same. Okay, so if it asks you to count the number of bit per symbol, you can easily use s over n, right? Which should be n over s, which is 16 over 8. So r become 2, or number of bit become 2, means that one symbol represent 2 bits. Okay, any questions so far? So you can interrupt me anytime if you cannot catch my presentation. Okay, let's take a look at an example to calculate bit and baud rate. And analog signal carry 4 bits per signal element. So one signal element contains 4 bits. So this is R, right? And if 1,000 signal elements are sent per second, this is baud rate, right? Baud rate is 1,000 baud. Find the bit rate. So it's very easy. By using this equation, you know R, you know S, then you can calculate N, which is 4,000 bits per second. And how about this example? The signal has bit rate of 8,000 bits per second. So this is N, right? And a baud rate of 1,000 baud, this is S. How many bits are carried by each signal element? So you can use this equation to calculate R. So in this case, N equal 8,000, S equal to 1,000. So R become 8 bits per baud or 8 bits per symbol. And if it asks you how many signal elements or the level do we need, you have to calculate L, right? L equal to the power of R. Then if you know R, right, from this answer, then you can easily calculate L, which is 2 to the power of 8. So you need 256 level. I mean here. So the level become 256 level to get one symbol contain 8 bits. All right. So it's very complicated in the design and implementation. But if you want to increase the data rate, you can consider to use a higher levels, a higher numbers of the levels. Okay, let's come back for modulation technique. This is the first technique called ASK, amplitude shift keying. Okay, we have 3 signal again. This is the input of modulator. This is the carrier, right, at the modulator, and this is the output. So the concept is the same as AM. The concept is the same as AM. Means that the amplitude of the carrier change according to the amplitude of the input. And in this case, the input become digital and it's binary. There's only 2 levels. So the output will have only 2 amplitude change, right? In this case, the peak amplitude of one signal level is 0. So around this area, right? This bit, this 2 bit. The carrier is the orange one, but if the input is 0, the output of the modulator becomes 0. It means the amplitude becomes 0. And the other is the same as the amplitude of the carrier frequency. So in this area where the input is bit 1, there's a positive voltage, right? And then by using the multiplication or multiplier, multiply 1 to the carrier will be the same, right? I mean, the amplitude of the carrier becomes same because whatever value is multiplied with 1, the output still same, right? So to conclude, it's very easy for ASK. If you have only like 2 level, we call binary ASK in this case, because the level is just 2 level. This is binary. And you want to use ASK. So it means that the output we will call BASK will have only 2 value of the amplitude. Depends on the bit that is sent. If bit 1, then the amplitude will be the same as the carrier. If it's 0, 0 means 0 voltage multiplied by everything becomes 0, right? So if you send bit 0 represented by 0 volt, then the output of the modulator become 0 amplitude. So this is ASK, BSK, specifically because there's only binary 2 level. All right, this is ASK. And then if you take a look, bandwidth, the bandwidth of ASK is proportional to the baud rate. So if you know baud rate and you know D is the modulation index, which is the ratio of amplitude A0 and A1. A0 means that in this case is A0 becomes 0 volt and A1 become like here, sorry, from here to here is A1. So the index, modulation index for BSK equal actually A0 divide A1. But anyway, you can use this equation to calculate the bandwidth, and you know how to calculate baud rate. If you know bit rate and you know the number of bit per second, then you can calculate S, and then you can calculate bandwidth. All right. And this is how to implement the BSK. The technique is very similar to AM. So you have just only multiplier. You have the original signal input to the modulator, and the oscillator generate the higher frequency of the sine wave, which is carrier frequency, and then the output becomes just these two multiplying with each other. Okay, 1 times A1 become A1. 0 voltage times any value can be 0. So this is things that propagate into the wireless channel, the blue one. Okay, let's calculate the bandwidth of ASK. So we have a available bandwidth of 100 kHz, which span from 200 to 300 kHz. Okay, if you draw a bandwidth of BSK, and it ranges from 200 kHz and lasts at 300 kHz. It's very easy to calculate the frequency in the middle, right? The frequency in the middle is the carrier frequency. Okay, so the bandwidth here from 200 to 300 is 100 kHz, right? As the question say, and then you easily calculate the frequency in the middle, which is the answer of the carrier frequency. So in this case, the carrier frequency is 250 kHz, right? And how about the bit rate? Huh? If you know the bandwidth, and if you assume that it's actually say that D equal 1, then this become 2, right? And then it asks you to calculate the bit rate. Okay, so this is the equation, you know D, you know B, and then you can calculate S, right? And S represent by N over R. And then finally you can calculate that the data rate or bit rate becomes 50 kbit per second. You can check again by yourself. It is very easy to calculate because we have only one equation. All right, let's move to next technique of modulation. We call FSK. It's similar to FM. The concept is the same. The different thing is that the input is digital. And in this case, it's binary digital because there are only two levels. And this is because it's two level, the bit rate and the baud rate become the same, right? One bit, one symbol composed of one bit only. Okay, so n equal to s in this example. Okay, let's see. You have input 11001. You have the carrier, and then this is the output of the modulator. We call FSK signal, and we add adjective as B because it's binary, right? The input is just two level. So we call binary FSK. If you remember concept of FM, what is FM, ka? For FM, the characteristic of the carrier that change is frequency, right? But the difference between digital and analog input is that for digital one, you have only two level of amplitude. Then if the carrier, the frequency of the carrier change, according to the amplitude of the input, then the output or BFK have only two frequency. So we can define that, in this case, we can define that bit 0 could be represented by F1. So F1 is equal middle frequency, original frequency of the orange one, minus delta F, the difference of F, And bit 1 could represent so bit 1, sorry, bit 1. Okay, we continue, okay? So bit 1 here, if you want to modulate bit 1 by using FSK, the frequency of the carrier would be represented by another frequency, say F2. So again, now digital have only 2 levels. By using FSK, the frequency of the carrier will change into 2 frequency. It can be changed to F1 if, in this example, if the bit 0 is sent. The carrier frequency will change to F2 if bit 1 is sent. You can take a look here. Okay. So this is bit 1, right? Actually, the carrier frequency is the orange one. But if bit 1 is sent, this frequency will be changed to F2. And then followed by bit 1. The carrier frequency will change to be F2. And if bit 0 is sent, the carrier frequency will change to be F1 as we defined earlier. And if bit 0 is sent, the carrier frequency will change to F1. And if bit 1 is sent, the carrier frequency will change to F2. So the output, the blue signal represent binary FSK. And then you can observe that this is the signal which have a constant envelope. And the thing that's changed is just frequency. You can see that this is, okay, you can count the number of cycle. This is 1, 2, 3, 4 cycle at one period, represent bit 1. And this also 4 cycle in one period represent bit 1. This is F2. And if bit 0, the frequency of the carrier will be another frequency, not F2 anymore, but it will be F1. All right. Okay. So in this example, okay, actually this is not carrier, but it's defined as F1. So F1 means the frequency if you want to send bit 0. And I assume that at this point of time is 1 second. Then you can count the number of cycle of the orange one, become 10 cycle, right? So in this frequency, this is not carrier now. So this is the frequency of the frequency of 10 hertz represent sending of bit 0. And then F2 is the twice, double frequency of F1. In this case, F2 in each period is 4, right? And then you have 5 boards in this case. So in total, number of cycle of F2 is 20 cycle per second, and then it is 20 hertz. So in this example, in this figure, you can see that the distance, the difference between two frequency is 10, right? 20 minus 10 become 10. And the difference between two frequency, which is F2 minus F1, represent 2 times of the delta F. And then if you calculate back, what is FC? FC is actually, okay, I can explain by using this line. Okay, let's take a look this frequency domain. Okay, so the FC is actually the carrier frequency. And then by using FSK, the carrier frequency will move to F1 or F2. And then if you see here, F1 is actually FC minus delta F. So from here to here, it is delta F. From here to here is delta F. And F2 is equal FC, right? FC plus delta F become F2. FC plus delta F. And you can say here that if you want to calculate the difference between these two, which is range from here to here, is actually 2 delta F, right? So 2 delta F, which is the difference between two frequencies, can be calculated from maximum, the F2 minus F1. Okay, this is just to show that how the bandwidth of the FSK will be, because the range of the spectrum become like two two bandwidth, right? So one bandwidth represent bit 0, and this part represent bit 0, that is sent, and this part represent bit 1, and then in total, by sending this blue signal, which is BFSK, you have to have the bandwidth from here to here. Okay, the bandwidth of FSK is quite large. So this is the equation to calculate the bandwidth of FSK. D is the modulation index. S is the symbol rate, and this is the difference between F1 and F2. All right, then you can calculate the bandwidth. Okay. So any question? And this slide just show the implementation of FSK. BFSK can be viewed as two separate ASK symbol. So if you remember, oh, I forget to explain that. ASK has another name, is called on-off keying. Amplitude shift keying, there's a two amplitude change according to bit 1 or bit 0, right? So if you take a look, the signal of BASK, there's our signal that is, we consider that is on. We send the signal, but if in this period, the voltage becomes 0 voltage, so it's like the channel is off, no signal is sent. So sometimes BASK is called OOK. OOK is another name of BASK. And yeah, this is OOK. And by implement FSK, you can view these two ASK. So one ASK is modulated with F1, and the second FSK, second ASK is modulated with F2. And then this is on, off, right? On, off. This is on, off. But after that, you sum up these two streams, okay? You sum these two streams, and then it becomes this output signal. So sometimes it have higher frequency, sometimes have a lower frequency. And then you can recognize from this analog signal that, okay, at the part of higher frequency, you can recognize bit 1. And lower frequency, you can recognize bit 0. And here, higher frequency, you can recognize bit 1. And this lower frequency, you can recognize bit 0. All right, so this is the FSK, frequency of the carrier change into two frequency according to level of the digital signal. Okay, any question regarding FSK? So if no, okay, this is how to calculate the bit rate frequency. This is similar to the previous example. You can take a look by yourself. Okay, I will shift to the new technique of PSK, phase shift keying. This is another technique that is used a lot nowadays. Is called phase shift keying or PSK. With PSK, as you may guess, that the characteristic of the carrier, which is the phase, will be changed according to the signal you want to send. Okay, let's see. For example, the simplest one is binary PSK. Binary means that you have only bit 1 and bit 0 to send and have only 2 levels of the electrical signal, right? And then you want to send this information with the carrier, And how about the output? The output of the modulator is that the amplitude of the carrier will be the same. The frequency of the carrier will be the same, but the phase of the carrier will change according to the amplitude of the digital signal. For example, if you define that the symbol of bit 1, whenever you want to send bit 1, the phase of the carrier will be 0 degree. And then you define that if you want to send bit 0, the phase of the carrier will change to 180 degree. And then this is the example of the output. This is the output,นะคะ. This is called BPSK signal. Why I can call that? Because the amplitude still same, the frequency of each symbol same, right? In one period, there's a 4 cycle, right? With 0, there's 4 cycle as well. But the thing that's a different between bit 1 and bit 0 is that the phase will be different. As you define here, if you want to send bit 1, the phase of the carrier will be 0 degree, right? So you understand, right? That this is phase of 0 degree. And then it depends on the frequency. If I ask you what is FC in this example, can you answer? If you observe this output, do you know carrier frequency? Huh? Can any of you answer? Okay, I'll wait for the question. What is the frequency, carrier frequency of this modulation? Can any of you answer? Am I? Are you still with me? You can answer in the chat box. Okay. Not sure if you're still here with me. Because, the way to check that better you understand is that I'll ask you to draw or represent the signal from like data stream, carrier frequency, and the modulation modulate that signal. So if you don't know what is the carrier frequency, it's kind of difficult to represent the signal in terms of drawing a graph. Can any of you answer what is the frequency of the carrier in this case? What is carrier frequency? How do you know that? You see, this is 1 second, right? So you can calculate, this is very easy because you can count the number of cycle, right? How many cycle in 1 second in this case? 20, right? 1, 2, 3, 4, 4 times 5 baud, right? So in this case, frequency is 20 hertz. Okay. And then, okay, the baud rate is 5 because you use binary, baud rate and bit rate have the same number. Okay, note that one symbol or one signal element represent one bit. One signal element represent one bit, okay? One signal element. So you can send one bit at a time, one bit at a time. But if you want to send bit one, you cannot send bit one directly to the air, right? The things that accompany your information is the sine wave. So you have to draw the number of cycle. If you know, if I assume that, okay, the carrier frequency is 20 Hertz, and I give you the bit rate of 5 bit per second, you have to know how many cycle to represent bit one by sending bit one, because this is one signal element. So in total, I mean, in 1 second, there's 20 cycle, right? Because it's 20 Hertz. And then if you know that there's a 5 bars, or there is 5 bit per second. So you have to imply that for sending one signal element of carrier frequency of 20 Hertz, you have to send 4 cycle, right? 1, 2, 3, 4. 4 cycle represent one signal element. And if you want to send bit 1 again, there's a 4 cycle. If you send bit 0, there's a 4 cycle, but the phase is not same, because you define that if you want to send bit 0, the phase will be 180, right? So here, this is 180 degree when you want to send bit 0. But anyway, if you want to represent in time domain, you have to draw it in one cycle with the phase of 180 degrees. All right. And then 0 again at the beginning of the period of this signal element. This is bit 0. And you define that bit 0 has a phase of 180 degree. So still, you can continue from the phase of 180 degree, and you draw 4 cycle. And then next, you want to send bit 1, and you define that bit 1 have the phase of 0 degree. So whatever previous signal element is, what is the its phase is, you just ignore it and then start with this information, which is bit 1. And you define that with bit 1, the phase of the carrier will change to be 0 degree. And then you draw again 4 cycle. Why do you know 4 cycle? This is the hint, right? If I give you the frequency of the carrier equal 20 Hertz, and I give you the bit rate or baud rate, and then you can calculate the number of cycle that represent one signal element, right? In this case, you have 5 bauds, right? For each baud, you have to divide 20 by 5. So it means that for sending each baud, you have to send by 4 cycle of sine wave, because the frequency is 20 in total. Any question? So this is a bandwidth of the PSK. Okay, this is a modulation index also. It should give you, what is it, in the problem or question, and then you can calculate the bandwidth. Okay, so this is recall. I mean, the bandwidth of PSK and ASK are the same. So if I ask you to design the system that have spectrum efficiency, higher spectrum efficiency, you can consider to use PSK or ASK. Because of what? Because by having FSK, the bandwidth become like plus something, because you need at least two frequency in between, and then you have this separation. So you need a higher range of the bandwidth. So in terms of bandwidth efficiency, FSK may not work well. So in that case, if you consider about spectrum efficiency, you may consider using ASK or PSK. But for FSK, the good thing is that it's quite good to work with the noisy channel. So yeah, it depends on the objective of the usage. Okay, so all right, so actually by using PSK, there's not only be PSK, but there's many. I mean, if you, okay, I'll show you this constellation. So this is the graph that represent amplitude and phase of the phase shift keying modulation. Is called constellation diagram. This diagram, X, Y, or two-dimensional graph, represent phase and amplitude. By defining this, by using this graph, if I draw a circle here means the position of the symbol. So this one symbol, and the length from 0, coordinate to this symbol will represent the amplitude of the analog signal of the PSK. And the angle from x-axis to this line become a phase of PSK. So if I draw like this, okay, let's see here. This is two constellation diagram. If I draw only two circles in a graph, that means there are two pattern of symbol, and one symbol represent only one bit. Okay, so this is binary one. You have only two circle, and this is also two circle in the constellation diagram. Each circle represent one symbol composing of one bit. So the difference between these two is that, okay, let's take a look the above one first. If represent like this, bit 0 is at the 0, coordinate. So means that there's a no amplitude, right? No amplitude. Because the amplitude is measured from 0, to the circle of the symbol. But if the symbol is just here, there's no length between 0, to the symbol. So the amplitude is 0 in this case,นะคะ. But if you take a look here, this circle, you measure the length from 0, coordinate to this symbol. So if you want to send bit 1, the amplitude of the analog signal will be this length. And then this is a representation of this definition. This is actually ASK,นะคะ. So there's only one amplitude change. Actually, two amplitude. One amplitude is here, say A1, and another amplitude is A0, which is becomes 0 in this case. So there's one amplitude. Oh, sorry, there's two amplitude, A0, A1. But these two circles have the same phase, right? Because it's aligned in the x-axis. The phase, what is the phase up here? Huh? So the phase up here is 0, right? This is pi over 4, right? This is pi over 2, and so on, right? But if this 2 is in the x-axis, this is no phase change, right? Between here and here, two circle of symbols represent phase of 0 degree. So this is the constellation represent ASK. You can see here. If bit 1 come, if bit 1 come, the phase become 0 and amplitude become the length from the 0, 0, right? So the amplitude become A1. And if bit 1 come, the phase of the carrier become 0 degrees, still the same phase. And then the amplitude is A1. And how about bit 1? Oh, sorry, bit 0. Bit 0, this is represent bit 0 at this coordinate 0, 0. Phase is 0, amplitude 0, right? So amplitude 0, phase 0, so no signal sent. And then if bit 1 again, the length is the amplitude, A1, right? And the phase is 0 degree. You see, this is 0 degree. So this constellation represent ASK modulation. There's a 2 amplitude with only one phase of 0 degree. And how about BPSK? In this graph, you can see that there are 2 symbols, right? And this symbol represents bit 1. This symbol represents bit 0. How about the length from 0, 0 to 1? This is A, and this is A also, because the length is the same, right? So it's the radius. This is the same. So whatever the signal bit is sent, either 0 or 1, the amplitude of the carrier are same, which is A. But the things that are different is phase. At this position, the phase is 0 degree, right? Because there's a node angle with the x-axis. But how about this one? The angle from x-axis to here is pi radian or 180 degree, right? So whenever you send with 0, the phase of the carrier will change to be 180 degree. But whenever you send bit 1, the phase will be changed to be 0 degree. Both bit 0 and bit 1 have the same amplitude because there's the same length from the 0, 0 coordinate. You can see here. This is a sequence of the data. Okay. 1, 1, 0, 0, 1. So if bit 1 want to send, the phase of the carrier is 0 degree, right? So this is 0 degree phase. And the amplitude is A. So this is the height of A, voltage. And the number of cycles, it depends on what is the frequency. And in this case, the frequency is 20 Hertz because there are 5 boards. And then each signal element represents 4 cycles. So the frequency of the carrier is 20 Hertz in this case. But anyway, the constellation does not show the frequency. It shows just the amplitude and the phase. Right? So I hope you understand. So this 0, bit 0, if you take a look at 0, you want to send bit 0, the phase is 180 degree. Okay? You see? The phase in this position start with 180 degree. How about the amplitude? Amplitude are same. The amplitude is same as the bit 1 sent. So it's constant amplitude. All right. So in this case, this constellation represent the definition of symbol of bit 1 and bit 0. How about 4 cycle? 4 cycle means that there are 4 patterns of the symbol. 4 patterns of the symbol means that inside symbol can be 2 bits, right? From 0, 0, 0, 1, 1, 0, 1, 1. There's a 2 bit per each symbol. So in this case, it is called 4PSK. Because of what? Because there are 4 phases change according to 4 pattern. You define here in the constellation that symbol 00 represent phase of 0 degree. And then here the symbol 01 represent phase of 90 degree. And symbol 11 define the phase of 180 degree. And symbol 10 represent phase from x-axis to here, which is 270 degree. All right. So each symbol represent one phase. There are 4 phase change with this 4 symbol. So this is called 4PSK. By using 4PSK, I can say that the data rate can increase twice, 2 times, right? Because when you send in one period, you can send 2 bits at a time compared to BPSK. And then how about this one? This one, okay, this is wrong, okay? So remove this one. It's actually PSK. Q here is called quadrature. It's actually one type of 4 PSK. There are 4 phase change according to 4 symbol. So these 2 graphs are different in terms of the symbol start from like not 0 degree, but start from pi over 4. And then this is t pi over 4. So it's like it changed 4 phase also, but it's not start from 0. So this is kind of like a 4 PSK as well. And then if you take a look this constellation, you can see that this is 4 symbol, right? So the number in front imply the number of pattern of symbol. So there are 4 pattern of symbol. 4 pattern means there are 4 cycle in the constellation. And if this 4 cycle, right? So in each circle, this circle represent 2 bits. And how about this one? 16. 16 means that in the graph of constellation graph, there are 16 circle or 16 pattern of the symbol. So in each circle can represent 4 bits. So when you want to send the information in one period, you can send 4 bits at a time. By using 16, I mean the higher number, you can send higher data rate. But that's a more complicated because of what? You can see from here. This is 4 pattern, right? How many amplitude change? Huh? So this is 3 amplitude change, right? 0 amplitude, A1 amplitude. This is A1 as well, and this A2. 3 amplitude change, and there are 3 phase, right? In this case, phase 0 degree, pi over 4 degree, pi over 4 radian, or 45 degree, and 90 degree, or pi over 2 radian, right? So in this constellation, 3 phase change and 3 amplitude change. This is another technique of modulation we call QAM. I will not go into detail, but I just want you to like understand in the overview that if you want to increase the number of bit per symbol, it can help you achieve higher data rate, you can do it using a higher modulation called QAM. So you can like design the phase that change for phase. This is for QAM or for PSK. This is the same. Because QAM means that both phase and amplitude change, but in this constellation, the amplitude are same for each symbol, but the phase is changed for phase. And how about this one? This is for um, circle or for pattern of symbol as well, but the amplitude, how many amplitude are in this case? One, A1 is shorter. This is A2, A2, and this is the largest amplitude, is A3. So in this case, there are three amplitude. And how about phase? Phase, you have, okay, I can draw by using another color. So for the phase, this is one phase, right? This is another phase because different degree, and this is another degree, right? So there are three amplitude and three phase in this constellation. And for 16 QAM, there's many, right? The amplitude are three, right? One, two, three. For every quadrant, there are three amps, but the phase is quite complicated because each quadrant have three phases, right? But you have four quadrants. So in total, by having 16 QAM and draw constellation like this, in total, there are 12 phases with three amplitude. So this is kind of complex in terms of in terms of implementation, but it can help you to increase the data rate. Okay. Okay, I try to finish for PSK. I uh, I mentioned earlier that by having four symbol in a constellation, you can increase bit rate because you can code or send to 2 bit per one signal element, right? But in this case, for PSK means that it provides four phase state. One phase state corresponds to one symbol. So you can like define that for bit for one symbol like 00, you can represent the phase of 0 degree. And if the symbol of 01, you can define the phase of 90 degree. And if 10, you can define the phase of 180 degree. And for 11, you can define the phase of 270 degree. So it depends on your design, what phase should be represent each symbol. Okay? But anyway, this is more spectrum efficiency, but more complex receiver as well. But the good thing is that you can have 2 times of bandwidth efficiency, means that with the same bandwidth, you can send 2 times of the information compared with the BPSK. Okay. So actually, what difference between for PSK and QPSK? Actually, QPSK is one type of 4PSK. If I draw a constellation, 4PSK can be like starting from 0 phase like this, but the symbol pattern will be in sequence like 0, 0, 0, 1, 1, 0, 1, 1. So it's like change 90 degree each for each symbol. But for QPSK is a little bit different. At the position of 0, 1, and 1, 0, the phase will change 180 degree. 180 degree. Like, for example, here I start with 0, 0 with 0 degree phase, and then 0, 1 with 90 degree phase. But for 1, 0, instead of putting 1, 0 here, QPSK will make a transition to 180 shift of phase. So this is 90 degree, but 10 become minus 90 degree, and 11 become here 180 degree. So there's a reason of making it like this, but I don't want to explain in detail, but I just want to let you know that QPSK is like a one type of 4PSK, and there's a better issue that is make the communication better than just using like this chip of phase นะคะ but anyway the phase of the carrier change 4 times, which are the same as 4PSK. All right, so this one is just to show that by sending the QPSK, in QPSK, the bit stream is parallelized to each branch like this. This is the original bit stream, but it divides the branch of sending into 2 branches. For above one, it send the odd bit, and then the lower one is send the even bit. Okay, so for the above branch, it will be modulated with the frequency of the carrier, but you can observe here that it's not function sign, it's a cosine function, but it uses the same frequency, which is FC. And for the below branch, this stream is modulated with a sine function with the same FC. Both here is the carrier frequency with the same, is a carrier signal which are the same which have the same frequency, but the function are orthogonal. The word orthogonal means that sine and cosine wave never mix up with each other. It can use the same frequency of FC to modulate these 2 bit streams at the same time. But the signal will not mix up with each other. To say it simpler, you can send the information by having only same frequency, but you can send 2 bits at a time in one frequency. One bit is mixed up with the cos, and another bit is mixed up with the function sign, and then sum up together by sending the information out up to the channel. It can carry double bit compared to just send the binary information. Okay, so carrier in 2 branches are orthogonal, which is sine and cosine. 2 independent modem operate over the same bandwidth. So with the same bandwidth, with the same spectrum, you can send more number of bits. Specifically, so you can send twice of the information. This is a good thing of the 4QPSK or 4PSK or QPSK compared to BPSK. Okay. So this is like I explained, this is another version of the graph to represent how QPSK is implemented. Okay, so this is another version, advanced version of the QPSK. This is called pi over 4 shift QPSK. So it means that it uses both constellations like this. I can draw 2 constellation, this one and this one, and this mix up together, and then finally you can have 8 constellations. So this is 0 degree, 45, 90, and then 135, 180, and so on. So by having two constellation of QPSK, you can send so in this case there's eight circle, right? Eight circle, so it means that you can send like more number of bit at a time, so you can get the better data rate. Okay, so this is another version or advance of the QPSK. This is called Pi over 4 chip QPSK. This is used a lot in the modern communication, especially in cellular system. Okay, this is just I explained already the advantage of the Pi over 4 QPSK. And this is the example to calculate the bandwidth. You can use the bandwidth listed in the previous slide, and you can calculate an answer to the question. So that's all for today.